What is conservation of momentum? Conservation of momentum is the constancy of momentum. So which means that momentum is going to remain constant. So what conserves momentum? The absence of an external force acting on an isolated system. All right, two more definitions, guys. Elastic collision and an inelastic collision. Collision is elastic. In every single collision, momentum is going to be conserved. Every single collision is going to conserve momentum. If it's an elastic collision, kinetic energy is also conserved. If it's inelastic collision, the kinetic energy is not conserved. So elastic collision is going to conserve kinetic energy. Inelastic collision will not conserve kinetic energy. All right, so you got two objects approaching. There's the collision. In the collision, the momentum is going to be conserved. If it's elastic, kinetic energy is also going to be conserved. If it's inelastic, the kinetic energy is not going to be conserved. All right. So every single collision is going to conserve momentum. If it's elastic collision, kinetic energy is going to be conserved. If it's inelastic, kinetic energy is not going to be conserved. I guess put down your responses in the chat. Cool. If the kinetic energy is conserved, what do we have? It's going to be an elastic collision. Very good. All right, so pick out the best answer. Going once, going twice. All right, so if it's elastic collision, kinetic energy is going to be conserved. Once again, I guess for
defensive back Dwayne Starks knows the technique of tackling. Professor Louis Bloomfield knows the physics.
A runner carries with him a quantity called momentum, which is a measure of how hard it was to get him moving. A tackler's job is to try to take away that momentum, slow him down, or redirect his momentum so he loses yardage. Now, the runner isn't going to sit still. He's going to keep trying to build more momentum, so the tackler has a hard job.
Basically, you want to beat him to the punch, and you want to get as low as you can. But you don't want to get too low unless you're just knocking down his, taking his legs from under him.
A tackler doesn't always have to absorb all the player's momentum to stop him. He can transfer or redirect a runner's momentum into another direction. For example, if a tackler trips a runner, the runner falls to the ground, so his momentum is transferred to the ground.
And you want to explode with your hips as well and raise up into him so you can get a good contact with him.
When equal mass is hit head-on with the same momentum, it'll stop cold because each one absorbs the other's momentum perfectly. Or, if a runner is running close to the sideline, the tackler doesn't even have to hit the runner with enough force to stop him. He just has to hit the runner with enough force to redirect the runner's momentum.
okay,
So it carries him out of bounds.
On the line, the players' weights are roughly equal and they move at the same speed. But often a small
okay, guys.
There is always he'll stop cold because he's the ground, so his momentum is transferred to the ground.
All right, so a couple of questions.
Basically, you want to beat him
All right, so isolated system in this case, these two guys.
to the punch, and you want to get as low as you can. But you don't want to get too low unless
When equal mass is hit head-on with the same momentum,
Again, the isolated system is going to be these two guys colliding.
he'll stop cold because each one of them, for example, if a tackler trips
Isolated system is going to be
a
two
runner,
guys.
the runner falls to the ground, so
Then isolated system is going to be three
his
guys.
momentum is transferred into the ground.
And then when you have more people coming in, obviously the impact is going to have different impacts happening.
you want to explode with your
Out of bounds. Hard to player loud sound and potential for.
All right, another thing is type of collision that takes
So,
place.
Professor, where does energy figure when they hit? Which accounts for the loud
All right, so what's happening? Is this elastic or inelastic collision?
sound and potential for injuries?
Every single collision, the momentum is going to be conserved, obviously.
when lines collide, they release
Real life collisions are inelastic collisions, guys.
roughly 12,000
Which means that energy will never be conserved. Kinetic energy is never conserved.
joules of energy.
All right, so number one, when there's impact, what happens?
Momentum to the quarterback.
There's going to be
The
sound.
quarterback finds himself
There's going to be deformation.
moving in the direction of the line of momentum.
So the real life collisions will be inelastic. Kinetic energy is not going to be conserved. Real life collisions are inelastic, so kinetic energy will not be. All right, so case in point, let's do a simple example. So this is problem number 5. So what do we have? We got a halfback, and so he's running at 8 miles per hour. So he's gonna break away for a touchdown, and he's gonna get tackled from behind by a cornerback. This guy is running at 8 miles per hour. Cornerback is running at 12 miles per hour. So, which means that the cornerback is gonna catch up to him and then just gonna take him down. All right, so the halfback is gonna be 200 pounds. You've got a cornerback which is 150 to 80 pounds. All right. All right, so this is the halfback and this is the cornerback. All right, so this guy is going to catch up with him and then he's just going to tackle him down. So as soon as he tackles him, what's going to happen is they will have a common speed. So they're going to be moving in the same direction at the same speed. That's what's going to happen. So the question is, what is the speed after the tackle? Immediately after the tackle. So it's going to be an isolated system of the isolated system of 2 football players. All right, so this is the total momentum before the tackle. This is the total momentum after the tackle. After the tackle, both of them are going to have a common speed. So both masses are going to move together. That's what it means. So this speed and that speed will be common. So I'm just going to pull it out. And then divide both sides by the common mass. And that's it. So we end up getting an answer formula and then plug the numbers in. And when you plug the numbers in, it's going to give you about 10 miles per hour. All right, so that becomes the speed after the tackle.
Jesus! Come on, lucky pass. All right.
Elastic or inelastic collision? It's still inelastic, right? Kinetic energy is not conserved. How do we know that? There's a dent here, so during the deformation, you guys heard the sound. How much is going to be? All right, so real life collisions are inelastic.
Jesus!
And
Come on, lucky pass.
the movie version of someone getting shot.
All right. Move it. Keep it moving. Got it? Keep it moving. Move it. Keep it moving. Move it. Keep it moving.
Like I said, this movie is fairly realistic, including the shot.
Got it.
In real life, someone getting shot is not impressive. You're not going to see a lot of motion when somebody gets shot. No one is going to be flying in the direction of the bullet. All right, let's illustrate that case. The person who's getting shot at, if the bullet goes through the body, the person barely reacts. It's kind of weird. No one is going to be flying in the direction of the bullet. It's nothing like the way they portrayed in the video games, and it's nothing like what you guys see in the movies for the most part, with the exception of that movie, Saving Private Ryan. All right, so case in point, you got this bullet being shot into a target. Target is 70 kilograms, so you got 70 kilogram, 150 pound target that you're looking at. So the common bullet, the muzzle velocity is going to be 800 miles per hour. It's going to end up losing almost half of its speed as it's going through the body, in essence. Okay, just to check to see how much the body is going to move, this mass is going to move, you can just place this target stationary, a completely frictionless surface. All right, you just place it on a frictionless surface, and then just fire a bullet in it. Just one single bullet, check to see how much it's going to move. All right, so that's what we'll do. So you got the 70 kilogram mass, 150 kilogram mass, 150 pound mass. Okay, so that's like weigh 150 pounds. So that's almost like me. And the bullet is going to go right through this person. Imagine that it's a person on a frictionless surface. How much do you think that the person is going to move, or how fast the person is going to move?
Who's in jail now says he was so drugged with painkillers for a bad back
Before we do the calculations, let me show you a real life shooting.
that he doesn't remember the shooting, but he has seen the video.
It's me, it's my body, but it's not my mind, really.
Stryer claims the shooting was the result of months of growing frustration over a $100,000 trust that
So this guy
was for his
got the gun, and the other guy's being
medical
shot at.
treatment. Jerry Curry
Believe it or not, guys, this is
was the
blank point.
lawyer handling the trust. Stryer says on the day of the shooting, he was already
It's a point blank shooting.
drugged up of growing
Every time he's firing a gun, the other guy's getting hit. That's what I'm getting.
frustration over a $100,000
The other guy's not flying around. He's not going down.
trust that was for his medical treatment. Jerry Curry was the lawyer handling the trust. Stryer says on the day of the shooting, he was already drugged up and frustrated when he left the courthouse following the latest hearing on his case.
So I went out, took more pills, and I became pretty weak at that point.
He also took 2 handguns out of the trunk of his car.
It was like a dream opening up the trunk. Something happened to me, and I can't explain it.
Stryer and his lawyer say he's innocent of attempted murder, and the video proves it. They maintain that no sane person would shoot someone in such a public place with TV cameras rolling.
It supports the defense position that he was in a psychotic state, completely and thoroughly. He was totally oblivious to everything around him. He was acting totally irrationally. Nobody in their right mind would make such a plan.
That's not something I would do. You know, shooting somebody in cameras. Never would I do something like that.
The defense brought up that theory at Stryer's trial. The prosecution didn't buy it.
It was nonsense. He was not stumbling. He had no problem handling the gun, putting it away.
The jury found Stryer guilty. He's to be sentenced later this month, and at the age of 66, he'll most likely spend the rest of his life in prison.
Somebody should have stopped me, because evidently I wasn't able to stop myself. And I just wish somebody would have stopped me in some way. I had no reason to shoot the man.
Jerry and Ro Curry, who have 3 daughters and 2 grandchildren, say they forgive Stryer, but they'd like to see him locked up.
I don't want him to be let out. No, I don't. because I don't know what he would do. He would probably still come after us.
Curry, who's made a full recovery, says the attack and the video have changed his life.
You appreciate your life a lot more. You appreciate the small things in your life you kind of take for granted.
Anyway, so let's check to see what happens. So that's the problem. So we got the bullet. He's going to be shot at 800 miles per hour. So that's the muzzle velocity to your target, which is 70 kilograms. And it's going to emerge through the body. It's going to emerge from the body. It's almost half the speed. The target is not moving initially. So the question is, how fast will the target be moving on a frictionless surface after being shot? Okay, so we do the conversions. So figure out the speed of the target on a frictionless surface. All right, so it's an isolated system between the bullet and the target. So which means that momentum is going to be constant or conserved. So known as the conservation of momentum. Cool. So final momentum of a system is going to equal to the initial momentum of a system. All right, so initial speed of the target is going to be 0, so that term drops out. All right, so solve it for final speed. V sub 2 is what we're solving for. All right, so that's the speed of the target. So follow the rules of algebra at that point. And then come up with the final expression. And then plug the numbers in. All right, so you end up getting 600th of a meter per second in terms of miles per hour. As it's almost 1/10 of a mile. This thing is going to move, but it's going to move barely. It's going to be moving very slowly. That's what it means. Without friction. If there's no friction, yeah, this thing is going to start to move, but it's going to move very slowly. With friction, which means that the body's not going to move at all. And so that's what happens in real life.
Is that similar to the recoil?
Okay, hold that thought. That's similar to a recoil. Hold on. That's a really good question because that answer is coming up. All right, so how much is the kinetic energy change? So what's happening is obviously the bullet is going to end up losing kinetic energy. So how much kinetic energy is going to be lost by the bullet in essence? All right, that's what we're looking at. Changing the kinetic energy of the bullet. Bullet has an initial speed. This is the initial speed of the bullet. This is the final speed of the bullet. This is the mass of the bullet. Boom, boom, boom. Plug the numbers in. All right, so this is the amount of kinetic energy that the bullet is going to lose. And so that's the amount of kinetic energy.